Section 13.8 is Stoke's theorem. And Stoke's theorem is sort of an extension of Green's theorem to surfaces now. So remember that Green's theorem was an identity between line integrals and a line integral about a closed curve C and the region that's enclosed by that closed curve C in the plane. So that's a flat surface in some sense, or a flat region in the plane. And note that a surface itself can be a three-dimensional entity, and I've got something like that drawn below. So before we get into any of the details of this, let's look at this surface I've got below here. It's S is the name of this surface, and it is, it could be parameterized by some function R of UV. Two parameters is the name of the game there to make it a surface. But note that it does exist in three-dimensional space. This thing is sort of curved. It's kind of bean-shaped. Maybe we could really literally think about that as being the upper half of the shell of a peanut or a bean or something like that. Just to imagine that this thing does have some kind of curvature, and it wouldn't live in the plane. It's not flat. It wouldn't sit in the XY plane or any plane for that matter. And these normal vectors are kind of indicating that. They're sort of off in different directions based on the contours or the shape of this surface. So if this was a two-dimensional surface or a flat surface, in other words, a region in the plane, a planar surface, one might say, I guess, then we would have normal vectors that would all essentially point in the same direction out of the plane. They wouldn't be bent according to whatever the curves or the contours of this surface are. So that's the difference between Stoke's theorem and Green's theorem. Where Green's theorem worked for a region in the plane, say D, and its boundary curve C, which is just a flat region. Stoke's theorem actually works for a region for a surface which naturally lives in three dimensions, which really means it's a generalization. It's of Green's theorem, or in other words, Green's theorem is a special case of Stoke's theorem, and that light. So let's look at the details of this now that I've kind of emphasized at least what it's related to and what the geometry is. If we let S be an oriented piecewise smooth surface, and that's more or less what I've drawn below and looked at already, it's bounded by a simple closed piecewise smooth boundary curve C. Again, we see that we have boundary curve C drawn and labeled here, or labeled also as boundary S, the alternative notation. And it has positive orientation. We're moving counterclockwise as we look at it. If we do the right-hand rule, the curl, the normal vectors are pointing out of, pointing away from this, or upward, I guess we could think, from this surface as our fingers wrap in the direction. So our thumb points up as our fingers wrap in the direction of travel around this curve. So it satisfies the right-hand rule, so we're oriented positively as we look at this in the normal vectors. Okay, F is a vector field with components that have first continuous partials on an open region R3, and also it contains S. So most importantly, that anywhere inside this region of space containing this surface, F has continuous partials. And that's all we need for Stoke's theorem to hold. And this is Stoke's theorem. We'll notice that it looks a lot like Green's theorem, only the difference is right here. Rather than being that partial Q with respect to X minus partial P with respect to Y, we have the curl of F dotted with the surface normal ds. Of course, that we know how to handle that from surface integrals in section 13.7. There's multiple ways we can go about attacking one of these problems per that section. Written in terms of the boundary of S, using that notation with the following. Sometimes that's a bit more concise. To note that the boundary of S is, as used on the left-hand side of this equation, is the positive orientation of the boundary of S. So that's Stoke's theorem. There's the proof to it is in the textbook. It's got a lot of details in terms of calculation, so it's not highly informative. It takes a long time to get through all of those steps, and it wouldn't make for a very good video, but the student is certainly encouraged to work through the special case of the proof in the theorem. It involves a couple delicate chain rules that are applied, as well as a use of Green's theorem to help establish the Stoke's theorem, which might not be a surprise since Green's theorem is a special case of Stoke's theorem, so it could be used to help prove the general case. Okay, I'm more interested in getting us to work with what this thing actually is. Just to reiterate that idea that Stoke's theorem is a generalization of Green's theorem, let's consider the case where S is flat. As I said before, S is not necessarily flat when we consider Stoke's theorem, but in case it is, we'll see that this will reduce, that Stoke's theorem will reduce to Green's theorem, because if S is flat, it can be expressed as a region in the XY plane with an upward orientation traveling counterclockwise around its boundary. This is as we see off to the right here in this drawing. We're in the XY plane, coordinate plane. We have a region S that's flat and lives flatly in that plane. There's no z-axis here. There's nothing that sticks up out of that plane. It's got boundary oriented in the positive direction about the region S that it encloses. And we can use Green's theorem in vector form, right, from one of the last things we did in section 13.7 to come up with this identity as we have it here. And we note that the unit normal for this curve, it's the only key here, is how we find this unit normal from Stoke's theorem. Well, that is really, if we look at the plane here, the normal vector to anything in this plane is the standard basis vector k. 0, 0, 1 is orthogonal at any point in this plane, because that one sticks out of the plane orthogonally. Okay, so there's our normal vector. It essentially reduces to this special case when we're dealing with a flat region S. And with this, that curl of f dot k, that's the result that we did last time in section 13.7, I believe, or perhaps it was earlier than that. We've done it previously, though. So we recognize this as the vector form of Green's theorem. In fact, some of this is actually worked out down here. So this is the curl of f dotted with k. And the result is exactly this term. Well, that's replacing this in here, and we see that that is the known term for Green's theorem when we're given a function in terms of x and y describing the surface. Okay, so now let's get to using this result. So we've got the line integral of f dotted with dr, where our vector field f is given by the following, and c is the intersection of the plane y plus z equals 2 and the cylinder x squared plus y squared equals 1, with c oriented counterclockwise when viewed from above. So we get a positive orientation, and we're asked to evaluate this line integral. So we've got a couple of choices. We could try to do that directly. Since we're in Stoke's theorem, the section, it's probably most likely that we're going to want to convert this line integral into a surface integral. When you're not sure, and it doesn't tell you to use Stoke's theorem or something like that, then you might attempt one way, but always realize that you've got an out to try the other version. So you might try this first, but always realize you could switch over and try this instead. Sometimes, curiously enough, this integral, double integral, is easier to handle than this integral. So if you find that one of these, you begin either on this side or on the other side, and you find an integration that you're not actually able to handle, or setting things up becomes really difficult, you just might try the other version. So in this case, we're going to switch this thing over to a surface. And the reason we do that is we look at what we've got here. C is the intersection of a plane, this plane, and this cylinder. That can be tricky to parameterize. Of course, we can visualize it. It's going to be an ellipse, because if you imagine when a plane intersects an ellipse, it might look something like this. When a plane intersects a cylinder, it might look something like this. So the plane would be tilted, and when we slice through the side of that cylinder at an angle, we're going to get an ellipse out. Well, parameterizing what that is in three-dimensional space could be a pretty messy parameterization. So rather than even trying to do that, so this is a case where the setup might just give us more resistance than we'd like, we switch over and say, let's think about this as a surface. There's a surface formed by the region of this plane, which is inside this cylinder. And sure, it's an elliptic shaped surface, but we should be able to handle that. So in terms of a surface integral, and if we recall section 13.7, then in fact we will, and we'll see below that that will be the case. So this is easier to parameterize because after all, we're just going to use the projection of it onto the xy plane, and that projection is just the circle x squared plus y squared is less than or equal to 1. So perhaps I should have left that drawing I had before. I didn't intend to use a drawing here because we don't always need to think about this in terms of a drawing. But so we'll use this region D down below from our surface S, since that's the projection onto the XY plane. So perhaps that is a useful picture to have lying around. And we're using all points within there because this is a surface integral to integrate the surface integral. So let's see. We've got Stoke's theorem tells us that the line integral then is equal to the surface integral of the curl of f. So we've already started to expand this. I've swapped out D for S because we're going to talk about the normal vector, which is a vector that's normal to this surface here, right? And we've started to work directly with the curl of f as well. So once we start to put the details in, namely that normal vector, then we know that we can switch from S to that projection D. That's all packed into the formulas for these surface integrals that we've used in the past. And it's all essentially follows when we use it in Stoke's theorem as well. So first we calculate the gradient of, the curl of f. That's the determinant of this matrix. And we end up with this vector, 0, 0, 1 plus 2y. We calculate the normal vector. Now note that there is a formula for this if we really wanted to go about it. But what we've used in this case is that this is the normal vector to this plane up here, right? Even though it is an elliptic region in that cylinder, it's still a plane. Its normal vector should actually be a constant, right? But the way to find that generally is to use this parameterization that we'd have here. This is our, we could call it R if we wanted to. And to find the normal vector to it, we do, it's R sub x crossed with R sub y. So those are the vector partial derivative of this, the vector partial derivative of that with respect to x and y respectively. That's what we have here and here. And we carry that out. And to no surprise, we have a normal vector that's constant, again, because that's the vector that's normal to the plane. Now, this is the part, remember, that this dot product in these surface integrals is actually taken care of. We don't have to think about the surface anymore once we know its normal vector. Now we just apply this dot product with whatever our vector field is. In this case, we're using the curl of this vector field f, which is a vector field in itself, and we take this dot product. So these two calculations will always be done somewhere off to the side. Remember the normal vector one, this one has some formulas for it to make it a little easier if we like. I prefer to just do it from scratch each time. But we put both of those in. It's the dot product of these two vectors. And once we're here, we're really off and rolling, and this is not too bad. Notice we've left our region vague still. We're integrating over some planar region D with respect to the area. But once we calculate this, we might realize we might make a choice one way or the other about whether or not we want to change our coordinate system. And since we are dealing with a circular region or a disk, D, described by x squared plus y squared less than or equal to 1, then yeah, naturally we'll want to use polar coordinates. And it's at this step that we actually convert to it. So we leave everything sort of vague up here so we can make our decisions as we get closer to the actual integration of this. Once everything is set up, we realize that, yeah, if we swap out y for r sine of theta, this will be a fairly easy polar integral to handle. And that, in fact, is what we have here. 1 plus 2y becomes this term. And the formula for the polar integral is r dr theta here. We go from 0 to 1 in r to cover this full disk in here. And we go from 0 to 2 pi to follow it all the way around. So that makes up that full disk. And we're off and running. Once we've integrated all these terms, we end up with an answer of pi. This is a straightforward integration, first with respect to r, applying the limits of integration, then with respect to theta, and the result is pi. Okay, so this is a case where the line integral would have just been maybe a little bit more work because of all the parameterization that we'd have to do in order to get this ellipse. Or maybe we did go through that parameterization, and maybe it's not so bad, and students who remember section or chapter 10 quite well would be adept at doing this, but perhaps you do go through all the work of that parameterization, and then you realize that you have an integral that is just intractable, that it's just you're unable to evaluate that integral because it's too difficult or messy or something, and it would turn out that the surface integral would be a much nicer way to go. In fact, if we look, this integral was a pretty easy integral. So one trick we've got, and we may or may not use it, actually we will use it below, but one trick we've got is the following. If S1 and S2 are oriented surfaces, both satisfying the hypotheses of Stoke's theorem, and they have a common boundary, C, then we can be sort of tricky. We can switch from evaluating this double integral over the surface S1, linking it through Stoke's theorem to the line integral along its boundaries, and then equating that to the surface integral across S2, because of course they have the same boundaries. Since this side's equal to this side and this side's equal to this, we can jump between surface integrals. So that's a nice tool. I believe we've used that in Green's theorem before. If not, then we had something similar, analogous to it. So let's use that below in the next example, just because it's there. It's not necessary that we use that, but it'll be a good demonstration of it. So use Stoke's theorem to compute the integral, the surface integral of curl of f dot ds over S, where f is the given vector field here, and S is the part of the sphere with radius 4 centered at the origin that lies inside the cylinder x squared plus y squared equals 1 and is above the xy plane. Okay, so it might not hurt to sketch a little bit of that as well. Again, I think we're so used to seeing these things so many times that we all have a pretty decent idea of what this looks like. We've got a cylinder of radius 1. We got to be above the xy plane. This is z here. And then we've got a sphere of radius 4, and maybe it's quite a bit wider, but we'll do something like this just to make it easy to see. And then what we're dealing with is this spherical cap that's inside this cylinder. Okay, and we're looking to compute the integral, the surface integral of the vector field on this surface S right here. Okay, and that of course is given by Stoke's theorem, curl of f dot ds. So we could begin to set that up. I think the first challenge that we'll run into is to realize that S is in fact a surface, right? It's got a very distinct sort of round cap to it, right? It's a three-dimensional thing, right? We know that this thing is capped in sort of the top of a globe in some sense. We can think about that on top of a ball or something. So it's not going to be extremely easy to parameterize or get a normal vector for. However, if we think about the boundary of this thing, so the boundary of this region, of this surface, is given by C, where C is equal to this parametric function, or vector function, r equals cosine theta sine theta root 3. How did we get root 3? Well, we took the fact that x squared plus y squared equals 1, and we substituted it into the formula for the sphere to get 1 plus z squared equals 4. Z squared equals 3, so z is plus or minus root 3. We're only working above the xy plane, so we've taken positive root 3. Okay, so some steps that weren't shown, but we've done things like this many times by now. This three-dimensional geometry shouldn't be holding us back too much. So C parameterizes the boundary, but we also realize that our original surface S, the spherical cap, shares the boundary curve C, parameterized by this function, shares the same boundary curve as the disk S1 equals x squared plus y squared less than or equal to 1, with Z being equal to root 3. Okay, so in other words, it says take that flat disk, that's the projection of that spherical cap, onto the plane Z equals root 3. In other words, approximately right here, just a little bit below that. Let me try to draw a little bit below the top of that spherical cap. Okay, so Z equals root 3 right there. Gives us the disk that shares the exact same boundary with the surface S. And since it is a disk and it's flat, it's going to be much easier to describe it parametrically, or as a parametric surface. So what we've done then is started with our spherical cap S1, and then we realized, well, it's got a circular boundary, which is the same boundary as a disk that's the shadow of it at a certain height of Z, which is Z equals root 3. So let's just do that surface integral instead of the original one, because the normal vector for this one and all the work that this entails will be much easier to come up with than the original surface, or that spherical cap. So working through Stokes' theorem, here it is. Here's that transition, our original surface to the boundary curve, the line integral of the boundary curve, to our new surface S1, which is just the disk. Now, the disk is parameterized by the following. R of uv, u cosine v, u sine v, root 3. Should be noted that in addition to that, u is to range from values 0 to 1. To be exact. Now, v should range from 0 to 2 pi, but if it repeats itself, it just covers the disk again further. So we'll just remember to just go from 0 to 2 pi as usual. Now, the normal vector for this surface is, remember again, it's r sub u crossed with r sub v. So that's what's going on in this matrix determinant. It's a cross product, and we end up with a vector 0, 0, u in our uv components parameters. And then the curl of this vector field f, we're finally getting to that. Here's our vector field f input at the bottom of this curl matrix, and we calculate the curl here, and we've got the resulting vector on the right. Now we know that we take the curl and this normal vector and we dot them. That's what we see set up right here. And here we are inputting the curl vector dotted with the normal vector to our surface. The curl is the curl of the vector field, and the normal is the normal with respect to the surface that we're integrating over. And we see that when we compute this dot product, we have, well, the result is 0 for the dot product. So the surface integral over 0 is just 0. And of course, we didn't put the limits of integration in yet, but those would have been 0 to 1 and 0 to 2 pi to make up that unit disk S1 at the height z equals root 3. So none of that was necessary because the integral is zeroed out. In fact, the root 3 part isn't really even necessary either, because as soon as we take the derivative, that disappears. But to be very thorough about it, C needed to share the boundary, or C needed to be the common boundary of S and S1. So we had to move that disk up to the height of z equals root 3. Now, getting an answer of 0 in a problem like this could be a little bit alarming, and it's new for us to be looking at this theorem. So possibly the student might say, okay, that seemed a little fishy to me. This gives us a good opportunity, this problem specifically, to confirm Stokes' theorem. So in other words, and we don't quite confirm it because we don't actually do the surface integral for the sphere S. That could be an exercise for a student, but I'm not even sure if that's going to be a very easy integral to come up with, so maybe it's not a great exercise. It's worth a look. It's certainly worth setting up. But let's at least confirm this side of the identity, this and this. Okay, so if we got 0 out of our surface integral, then we should get 0 out of our line integral. So let's try that. And that would have been another alternative to solve this problem. So C is the boundary of this surface S. It's a circle of radius 1 at height z equals √3. So there's our circle of radius 1. Theta goes from 0 to 2 pi. And note that this is a positive orientation to have x be cosine theta and y be sine theta. As we look down at it from above, our rotation, our right-hand rule is satisfied and the normal vector points upward. Now r prime, because that's part of our line integral formula, is calculated here. And we're parameterizing everything in terms of theta, we'll note. So our line integral is f of r of t, which is this calculation, f of r of t. So x, y, and z are these three components plugged into the expression for f. So we'll see once we handle those details, we've got exactly what is in that vector. And then this is dotted with r prime of t, which we just have directly above, and we see how that should go. And now when we compute this dot product, we see that we again arrive at an integrand of 0, which in a single integral is just as well also going to be 0 in its final answer. So we've confirmed that it is at least true for this identity. And also if we were a student in doubt of an answer, we found another method to come up with something that supports what we found in our first calculation. So it's nice when the problem will work both ways. We can sometimes use a result like this to check our answer. Okay, so so Stokes' theorem tells us just a little bit about what this curl actually is. I've been asserting all along that the curl is a calculation about rotation, and so is the textbook at this point. So let's provide some deeper intuition on that using Stokes' theorem here. So suppose we've got V, which is a velocity field in a fluid flow, and we consider the line integral around an oriented closed curve C. So I've drawn such a thing off to the side here. So here's our oriented closed curve C. And the line integral of this velocity field around C or along C is rewritten as, remember that dr, vector dr, is the unit tangent vector ds, right? It swaps out with this. So if you go back to line integrals to look at that, you find that is in fact the case. So the line integral of this velocity field around C is actually equal to, this is v dot t is the component of v in the direction of the unit tangent vector. So we're sort of summing up all the flows, the components, the fluid flow v that's in the direction of the unit tangent vector. So note that the more aligned t and v are, the more fluid flow there is along this curve. In other words, right here, t and v are pointing in the same direction, though they might not have the same magnitude. So there is the most fluid flow we could get along the curve at this point. Whereas on the other hand, and so a dot product for vectors like that would be maximal. Right? Think about the dot product is proportional to the angle between the vectors, or the cosine of the angle between the vectors. In this case, the angle is 0, so cosine 0 is 1. So this is sort of a maximal component of v in the direction t, whereas if t is perpendicular to v, the dot product of that is going to be 0, and that means there's no fluid flow in the direction of the tangent vector of c. So there's no fluid flow along the boundary C here. And of course, this more arbitrary drawing right here is somewhat, there is some fluid flow along C, but it's not maximal like the bottom one, and it's not 0 like the one on the right. So anything could be the case here. And in fact, this could be a true vector field V here. Well, certainly is drawn as one. It could even be a conservative one if we wanted to, but we don't really need to talk about that necessarily. But this integral is really summing up the amount of circulation of the fluid flow around the boundary curve C, or around this closed curve C, and that's exactly what's defined below. So this integral actually represents fluid flow around the curve C in a vector field, or a velocity field V. So let's go in a little bit deeper to what's going on with this and relate it to the curl. So if we take a point P naught, it's a point in a fluid, or in the fluid, and we let S sub A be a disk around this point P naught. So here we have a point P naught down below, and S sub A is a disk with radius A around P naught. So here's our disk, and we're talking about including all the points in here since it is a disk. Arbitrary radius A for now, but we'll try to make it kind of small. So long as it is small, then we can approximate the curl of F all along, or all throughout this disk, as being the curl of F at P naught. And this approximation works out because the curl of F is continuous. So we have that stated here. Since it is, the curl of F is continuous, then we know that we're going to have continuous change of the curl vector anywhere in this disk. So it's going to be roughly close to what it is at P naught. And the smaller we make that radius, or that disk A, the closer we'll be to this approximation. So using Stokes' theorem and a quick little approximation for the circulation integral of V around the boundary circle C, we have the following. This is the moment here where we use Stokes' theorem. We go from the circulation around the curve C sub A, which is the boundary of the disk. Everything's oriented in a clockwise direction. And this is equal to, by Stokes' theorem, the double integral of the curl of V dotted with ds, which is, again, split up further, curl of V dot in, the normal vector with ds. And we can approximate this. This is where we're using this fact in this step here. Okay, so the curl of V dot dn is approximately equal to the curl of V at P naught dotted with the normal vector at P naught, thanks to these vectors being continuous. These functions, curl of V and n, are continuous. So this approximation is somewhat valid. Of course, the smaller we make the radius A, and consequently the disk S sub A, the closer this approximation becomes, or the more accurate it is. So realizing this, though, these two things are constant. The curl at P naught, V at P naught, and the normal vector at P naught is at a single point that's explicitly given. So that's a constant, and the integral of this then reduces to, using polar coordinates, r d theta from 0 to a, the radius of a, and then traveling all around 0 to 2 pi to make up the whole disk. And the result of that is this constant times pi a squared. Okay, and then lastly, what we do with that, so we conclude in this line that the curl of the vector field at P naught dotted with the normal vector at P naught is equal to the limit as a goes to 0 of 1 over pi a squared of the circulation integral. So what that's telling us is, at this point P naught, and I've drawn this so that the curl of V is equal to n, we have maximum rotation. If these two vectors are equal to each other, then their dot product is as large as it's going to be, which means that we have maximum circulation around this boundary. Now, so we can imagine that as if the disk I've drawn could be thought of as, the book uses this idea of a little paddle wheel or a propeller, but I could say maybe an anemometer, the little wind measurement device that you see sometimes on weather predicting equipment. If the vector that's normal to this little anemometer or paddle wheel is in line with the curl of the fluid flow, of the velocity field of this fluid, then we're going to have the maximum amount of spin. We're going to have the maximum amount of circulation. That's what's happening over here. This will be a maximum as large as this integral could be. Now, if it wasn't this way, in fact, if it was perpendicular, so if we had something like this, if the anemometer was placed the other way, we're talking about a different surface, perhaps oriented like this with a normal vector here. So the curl, so this is the normal vector n is now perpendicular to the curl of v. And if we think of it again as this anemometer, it's got little arms on it and little cupped half spheres that collect the wind or the fluid flow and turn in it. Well, it's not going to turn anymore. The fluid flow is traveling orthogonal to each of these little paddle arms, and it won't spin it in any way. So in this case, our circulation would be 0, and that is exactly what this says on this side, and it tells us that that circulation integral would be 0. So we notice that constant of a that's in there. Just to kind of make a comment about that, our circulation is larger and larger the larger the radius a is. And if you go back up to here, we can see where that's coming into play. As a becomes larger, we have more circulation. Well, that would make, as long as the vectors are somewhat oriented in the same direction, or have at least some non-zero component in common, that means we're just further out. Think of it as a moment arm in radial motion, radial acceleration. So that's it. That's a nice breakdown of what the curl actually tells us, particularly in a velocity field, but that extends in some general way to any force fields that we might consider in the future in a physics problem or otherwise. So that's it for Stokes' theorem. We've only done a couple examples, but most of the problems should be very similar to these examples. Also, there aren't a whole lot of examples, so be sure to master all of them.